Hi, welcome back to a new video. A lot of things we cover on this channel are around the topic of cooling, and this mostly involves also the topic of thermal conductivity. But there are a lot of myths around this topic, especially for example with upgrading parts, such as with this Rocket Cool upgrade Heatspreader, which is made out of copper. And then it's also commonly known that, for example, this Intel IHS or this AMD IHS, they are also made out of copper. So why would you need an upgrade Heatspreader? Like, how is this copper alloy maybe better than the alloy that Intel or AMD are using? And then, for example, in the past, I was also offering, together with Caseking, that was for the 8700K, we were offering upgrade Heatspreaders with lapped copper or also made out of very, very clean silver. So how could this improve your thermal conductivity, and how do you even measure this? That's what we're going to cover in today's video. This video is sponsored by Hetzner and their dedicated root servers. The AX line offers a wide range of servers depending on your required CPU power, storage and memory. It starts with the AX41, which features a Ryzen 5 3600 with 64GB of memory and two 512GB NVMe SSDs for €34 per month. The AX101 would come with 5950X, 128GB of ECC memory, and two 3.84TB NVMe SSDs for €94 per month. Of course, fully configurable with the OS you need, additional storage and gigabit connection. Find out more in the link below. What does thermal conductivity even mean? To explain this a little bit more in detail and also a little bit more simple, we will imagine a wall made out of copper with a length of 1 meter, and at the same time we imagine a height of about 100 meters and a width of about 100 meters. Now we want to transport heat through the length of 1 meter of our copper wall. The thermal conductivity of copper is at about 400 watt per meter and Kelvin. We could also say watt per 1 meter and 1 Kelvin. Kelvin is typically used to describe temperature differences. This means, for example, you get up in the morning and your room has 20 degrees Celsius and in the evening it has 21 degrees Celsius, then you would have a temperature difference of 1 Kelvin. Going back to our example with 400 watt per meter and Kelvin, this means we are transferring 400 watt through our wall. And at a given thermal conductivity, this means that we will have a temperature difference of the surface of the left side on the wall and the right side of the wall of exactly 1 Kelvin. For example, if we would have our wall made out of aluminium, which has roughly half the conductivity, so about 200 watt per meter and Kelvin, then we could only send 200 watt to maintain the max difference of 1 Kelvin between the surface on the left side and the right side. In summary, the thermal conductivity means how much energy we can pump through 1 meter of material while maintaining a temperature difference of the surface of 1 Kelvin from input and output side. Before we get into the entire topic and measure some of these things you can see on the table, I just want to explain how we're measuring this and how we're going to calculate the thermal conductivity. And that's why we have this tiny device, which basically looks like a digital multimeter, but it's far from that. It's a device that can measure the electrical conductiveness on the surface of a material, of a non-ferrite metal, which means that you can basically measure how good is the electrical conductivity of a metal with this thing. It sounds simple, it's also very simple to use, but I can tell you this calibrated device costs about €7,000. We're using this internally at Thermogrisy, for example, to measure conductivity and quality of different alloys we're ordering. For example, if we want to check copper or if we want to just check our liquid metal, for example. With this device and also this sensor right here that contains an inductor and also an additional sensor, we can perform an ECT, an eddy current testing. So basically the inductor in here, if you hold it against a different material, which is a non-ferrite material, then this is causing a primary magnetic field. This primary magnetic field is then causing the eddy current. The eddy current again is causing a secondary magnetic field, which you can detect with the sensor. So basically one magnetic field, current, second magnetic field, you can detect it, and this way you can detect the electrical conductivity of the material. Going back to the beginning of the video, you might ask yourself the question now, why are we talking about electrical conductivity with this sensor while we are actually looking for the thermal conductivity? And I can tell you it's pretty simple because both are directly connected. In metals, free electrons are responsible both for electrical and thermal conductivity. For metals, there's also a second part for the thermal conductivity, which is due to phonons inside the metal. Basically, you have tiny vibrations inside the material that are transporting the heat. But for metals, that is only a very small portion and can be neglected. So we can just purely go after the electrical conductivity. The relation between electrical and thermal conductivity is written in the Wiedemann-Franz-Law. You can probably tell by the way how I pronounce it. Those are indeed, or were indeed, German scientists. If we take this piece of copper, for example, and we will just look at normal metals for a moment. If you heat up this piece of copper, both electrical and thermal conductivity will decrease. The proportionality of this is written down in the Wiedemann-Franz-Law. This means if you know one, so you know the electrical conductivity, you can calculate the other, for example, the thermal conductivity. That's also what you can see inside this chart, where you can see on top both copper and aluminium and the thermal conductivity over temperature. It's very important that we always look at individual materials because they behave differently. For example, for copper and aluminium, what I just said definitely counts for them both. As you can see, if the temperature increases to the right, the thermal conductivity decreases. But if you pay attention to brass, which is a copper zinc alloy, you will notice that it just behaves completely different. And with increasing temperature, the thermal conductivity is also increasing. That is something you can observe for metal alloys, whereas for the pure metals, it just behaves completely the opposite. And that's something you can make use of, for example, for liquid metal alloys, let's say the thermal greasy conductor knot, because that's a metal alloy, and that's beneficial because if you increase the temperature, let's say for a mobile CPU, then the thermal conductivity will be better if the CPU is running hotter, so it's actually increasing in thermal conductivity. That is also the reason why we don't use it for liquid nitrogen overclocking, because if you run this at like -100 or -200, the thermal conductivity is really bad. And that's how you get to this equation. Basically, you have the thermal conductivity, which is called the lambda, and it is a product out of the Lorentz number, which is depending on the exact material, the temperature in Kelvin, and the electrical conductivity in Siemens per meter. And this conductivity is what we measure with our device. And to explain everything in a simple way again, we are measuring the electrical conductivity with this device, and it's directly related to the thermal conductivity, which means if the electrical conductivity is increasing, the thermal conductivity is increasing as well. Our surface conductivity meter is now set up and ready to go. We have different parameters we can read on the display, such as the conductivity. That is always in relation to copper. That's called IACS. So for example, we have 3 different metals right next to it. This is pure copper. This is rated with 100% IACS. Those 3 metal pieces came out from a lab and they are 100% precise. Like just a tiny piece of copper like this will cost you like 400 euro. That's because they are calibration tools. Then we have brass next to it with 7.16 and then titan, which is actually a very bad conductor with 1.05. And you can also read the frequency the tool is working with, which is 60 kilohertz. Now, if you just want to check it again, we can check brass. It's supposed to be 7.16. It's reading 7.14, so that's quite accurate. Going back to copper, it's reading 100.0, where it was reading 100.1. Where it was reading 100.1 before, and now it's reading 99.9. Back to 101. One aspect that's also important to know is the frequency you are measuring at with 60 kilohertz, and this is determining how deep you're measuring inside the material. This is a fairly low frequency. You can also go up into like megahertz region. If you go up into the megahertz region, then you're only measuring like directly on the surface, maybe like 0.01 millimeters on the surface. With 60 kilohertz, we're reaching a depth of about 0.4 to 0.5 millimeters. The good thing about this is if you have tiny scratches in the surface, then it's going underneath these scratches, but it's going not too deep. So we can also measure rather thin materials, and we can also measure materials that are like 20 centimeters thick. What you also have to know is that the surface meter has a temperature compensation. That means everything we're measuring is compensated to plus 20 degrees Celsius. This only works for a certain temperature range, but right now in plus 28 degrees Celsius, this is still completely fine. We also have a tolerance on this of 0.5%. That also explains if we measure something twice, it's maybe reading 99, second measurement it's reading 99.3, then 99.2. That is how you get those slight variations because of the 0.5%. But for example, if we change between the Intel and the AMD CPU and it's going from 99 to 95, that is a clear indication that there is a difference, because that is far outside the tolerance. One thing we cannot neglect is any kind of coating on the material, or like the nickel plating which you have on heat spreaders. Right here we have a 12900K that is lapped. We have a 12900K that is not lapped, so it's nickel plated. We have a 5600X that is nickel plated and a lapped 5600X. Now if we check, just for reference again, our 100%, which is showing 101. If we go to the Intel CPU with nickel plating, it's still very, very close to 100. If we go to the lapped Intel CPU, it's going close to 102. So actually the copper on the IHS of Intel is purer than our lab calibration one we have here, which is already a great sign. So that will definitely have a very good thermal conductivity. Whereas if we check the AMD heat spreader with nickel plating, it's going down to 94. Sometimes it's reading like close to, yeah, it's definitely going down. And if we read the lapped AMD CPU, it's going to 101.5. So there's almost no difference in the copper of both materials, as you can see. That is like measurement tolerance of the device, even though it's you can see it's repeatable. But if we check with nickel plating, there's definitely a huge impact. If we are now following the Wiedemann-Franz-Law and first starting with our copper reference that is listed with 100% IACS, we measured 100.1, which then equals a thermal conductivity of 388. The 12900K was measured with 101.7, and that equals 394. The 5600X was slightly lower with 101.5, which equals 393. But I want to remind you again that the conductivity meter has a tolerance of 0.5%, which then means if we take the tolerance into account, both Intel and AMD CPUs have the same heat spreader quality when it comes to the copper itself. However, it seems like the nickel plating is quite a lot thicker on the AMD CPU, which then results maybe in a little bit worse thermal conductivity overall. And now going back to the beginning of the video, we will take the RocketCool upgrade heat spreader and then just measure if this really is an upgrade or if it's in the end just the same copper. It's actually the first time that I have one of these RocketCool IHS. And now it kind of makes sense because there is a slight elevation in the center, which is to compensate for the indium solder sheet that originally exists on the 12900K. But if you want to replace it with liquid metal, it makes sense that you're compensating the height difference with this small elevation. Because otherwise, if you just compare the general shape of the RocketCool IHS versus a standard Intel IHS, there's like no difference. Like the size difference is 0. Again, taking the reference first, so it's 100.1. Checking RocketCool, it's 101.3. The RocketCool IHS in the end also has about 393 thermal conductivity, which means that it will just perform the same as a stock Intel or AMD IHS, but it has this additional elevation in the center, which will cause your IHS to sit closer to the die. If you want to replace your original IHS with this one and liquid metal, then you will get better results with this than with a stock IHS, because you will have a tinier gap between the die and the IHS. But just purely conductivity wise, there will be no difference. If you are doing some sort of research about thermal conductivity, maybe then ending up on Wikipedia, checking values of metals, you will definitely see on top silver, which is listed as the highest conductivity for metals. That's why I got one of these tiny silver pieces, which we are going to measure and check the thermal conductivity. Of course, checking our reference again. First, it's 100.0, then checking to silver, it's 103.3. 3.6. Now calculated the thermal conductivity of silver, you can see it's about 410. That's definitely a little bit lower than what you can find online. Sometimes you can find values around 420. The reason for that is that this is not as pure as what you can theoretically find. This is 99.90, but there is also like 99.97, 99.99. And the last few digits definitely matter when it comes to thermal conductivity. That's why this is only about 410. If you want to go higher, you have to check for higher purity. One more thing I want to test and highlight is gold, because a lot of people have the false assumption that gold has a higher conductivity than silver. You often see like HDMI cables or like audio cables that are gold plated. Also, if you check on the backside of your Intel CPU, for example, all these pads, they are made out of copper and they are gold plated. The reason for the gold plating is not the better electrical conductivity, it's just for protection against corrosion. That's the only reason. That's the same for all those connectors you have, like the HDMI connectors. It's simply because you always want to have the same conditions. You don't want to get your connector to be worse, because for copper, for example, like this one, if you touch it, it will corrode over time and your contact would be worse. And that's the only reason why you would use gold. But let's check the thermal conductivity of this. And if we check the gold, you will see it's almost 25% worse than copper. You can see with the calculated value of below 300, it definitely would not make sense to build any kind of cooler out of pure gold. It would make much more sense to actually use pure silver because of the high conductivity, and we will also get to a water block that is made out of silver. But before we get to that, we will take another look at some copper alloys, because even though they have a very tiny amount of additional materials, this will have a huge impact on conductivity. Again, we're taking our reference first. This is something that's called SF copper. That basically means that this has a percentage of 0.015 to 0.04 of phosphorus. Still, that means it's 99.9% copper, so you could assume that this is pure copper. But if we double check this, you will see there is a huge impact on the conductivity. Compared to this normal plate right here, that's something I just borrowed from Grizzly, that's something we would use for making water blocks, for example. This will give you 100.4, so that is 99.99, and that is 99.9. But you see that is a clear difference, even though the phosphorus in here is only 0.015%. Now we are getting back to the cuplex kryos, which is this water block from Aqua Computer, and this is basically a silver special edition. It's listing 0.925 silver edition on the back. You might also know this alloy as sterling silver. 925 means that it's 92.5% of silver, which also means that the rest is 7.5% copper usually. And we already learned that most of the alloys will not perform quite well, so I can tell you this will be a surprise. On the left we have the normal cuplex kryos, which is the standard copper version. If we measure this one, you can see it's a very pure copper alloy. The conductivity is great, so this will definitely have very good performance. Whereas if we measure the silver version, it's actually only reading 96.5. Now going back to our chart, we will notice that our silver cooler has a thermal conductivity of 390. And if you're now wondering why the silver block with an IACS of 96.5 can have a higher conductivity than, for example, the SF copper with 98.9, that is due to the Lorentz number, which is different for silver, and it's significantly higher for silver than copper. But still, if we compare it to the kryos copper, which is listing a 102.5 IACS, it's resulting in 397. Sheik joined us for the conclusion, but the video has been taking so long that she already fell asleep. Taking a conclusion about our water blocks, we have a clear winner, and that is the Aqua Computer kryos, which has the purest copper of all the materials we tested. It's better than all the IHSs, also better than any of the other raw materials of copper which we tested. At the same time, the biggest loser we have is also from Aqua Computer, and that's the sterling silver edition. With a price difference of 150 euro, because this is roughly 100, this is roughly 250, this product absolutely makes no sense at all. I just don't get why it exists, simply because you will pay much more and you will have worse performance, at least on paper. If you would measure it, because this is 390 and this is 397 conductivity, you probably won't be able to tell a difference. In theory, maybe it's like 0.1 degrees worse on your CPU. But to be fair to Aqua Computer, if you go to their website, they don't talk about the silver at all. I mean, they list that it's made of silver, but they don't even say that it would be better. They don't advertise this, so I don't even know why the product exists. I guess it's because people think it's made out of silver and then the conductivity must be higher. I guess that's an assumption a lot of people have, and that's why they're probably wasting their money on this, even though it's absolutely not worth it. Going back to the Rocket Cool IHS, because that's something I often read in comments. Just get your 12900K and put your upgrade IHS on there made out of copper. All the IHSs, all the products we tested have about the same purity for the copper. The Intel IHS, AMD IHS, they have the same purity as this one. So just by buying this, that's also made of copper, you will not have a benefit on temperatures. But what will give you a benefit on temperature is the elevation you have in the center, which will make the IHS sit closer to your die. And if you use liquid metal, it will result in better temperatures, and also this IHS should be more even than the stock Intel IHS. The only thing I don't understand is why is this not nickel plated? Because definitely liquid metal with the gallium will eat your way into the pure copper if it's not nickel plated. So that's something that's definitely missing on here. And also if it's a chemical nickel layer that is very thin, it will not have an impact on the overall performance of this thing. So yeah, don't really get it. One more thing I don't understand is when I bought this online on RocketCool, the IHS looked much different to this. It was also advertising that it has an increased surface area to the stock Intel IHS, which this is not doing. I don't have an issue with it because it's probably not going to help anyway. But it's just weird that I'm getting a different product than what I actually paid for. So that's pretty strange. I'm not sure if they just forgot to update their website, but yeah, something they might want to do for the future. All right, I hope you enjoyed this video about thermal conductivity, how to measure it, how everything is explained, and yeah, it was a long video. Hope you enjoyed it. See you next time. Bye-bye. And the proportionality, proportionality